Sure. My name is Neil Vacharajani. As Matt said, I've been here for quite a while. I've been at Pure for about 4 years now. As I said when my mic was off, I'm on the engineering team. And so I want to talk a little bit today about how the whole thing is built. I am doing a whiteboard presentation. I've managed to avoid making slides for most of my time here, and I think the whiteboard's more interesting. It's also more interesting if you ask me questions rather than me just rambling on the whole time. So from 10,000 feet, I really want to go into some detail on the points that Kix raised when he was giving you the broader overview. In particular, how is it that we can make Flash affordable? If you look at some of the things that we're going to talk about in making Flash affordable, it's going to raise questions about how we make it available or reliable. Of course, there's the normal concerns that go on right there about how do you make things available and reliable, just the normal storage array questions. But there's going to be also things about how we make it affordable, which I think is going to create some novelty and some interest here, right? And then a little bit about what does this all mean for performance. At the end of the day, these are sort of the things you have to take care of, but part of the reason that you buy Flash in the first place is because of performance. But a peer to performance that we've found equally valuable is simplicity. So really, I'm almost ending here with what do you get? And I'm opening with why should you even consider it? If that makes sense. So what is the overall architecture of the storage array? This hopefully hasn't changed from the last time we did this. We have, I'll draw it right underneath here. We have storage controllers. I'm going to label them. These guys are commodity x86 servers. And they talk to each other over InfiniBand. No rocket science here. And then what do? We hang a bunch of Flash. And we talk to that Flash via InfiniBand. Once again, not a whole lot of rocket science here. But we've already begun to dive a little bit.
You just write SAS?
Yeah, serial attached SCSI.
You mentioned InfiniBand.
Oh, you just said InfiniBand.
Sorry, InfiniBand between the controlers, serial attached SCSI,
cool.
SAS,
all right.
no extra A for the other meaning of SAS, between the controllers, and I should draw a link here, between the controllers and the storage shelves. But even though this is not rocket science, we've already gotten sort of into that first layer deep into how do we make this whole platform affordable. Right? And you can see that these are commodity off-the-shelf components. This down here is also commodity off-the-shelf components. So we're taking standard x86 servers, we're taking standard off-the-shelf SSDs, and we're integrating them into a system. To be more specific about what is the Flash that's in here, it's consumer-grade MLC Flash, or what's come to be known as CMLC. And I'll go into some details of what that means. I think the names and versus what the product actually is are probably, the names aren't as good as they could be. I mean, heck, multi-level cell, apparently multi only means 2. And when you went to beyond 2, they needed to change that letter to T, to TLC. At least they admitted there that it only means 3.
So how far away do you think TLC is in general for storage, like storage arrays like this? And how far away are you guys?
That's a great question. So TLC has a bunch of interesting properties. So one, today in the marketplace, if you go and try and buy TLC, it's actually not that much cheaper dollar per gig than MLC. So The reason why I don't think you see it in widespread deployment anywhere is because it doesn't make economic sense. But the second aspect, and I think that this is what's really interesting about TLC, is that its read performance is comparable to MLC. Its write performance is the thing that actually suffers compared to all the flavors of MLC that are out there. What that means is that if you build your architecture appropriately, it actually is a fantastic storage media for flash storage arrays. And so for us, we're really waiting to see the trends in economics point to where it makes sense to integrate it. And at that point, we'll start revving our software to be able to take advantage of it.
Do you plan to use the TLC as a secondary storage, so building something new instead of only a one-tier storage today, or?
So the question is, are we going to use TLC as a secondary tier of storage? And so really everything, how we use it is all speculative, because ultimately at the end of the day, it comes down to characterizing the SSDs. So even when we use these consumer-grade MLC drives, we don't go to Fry's Electronics and just grab whatever drive they happen to have on their shelf. Our system is carefully tuned towards the innards of each of these SSDs. That's how the flash is organized, how the firmware behaves, etc. We want to tune our software stack to that flash. The word tier also, I think, comes with it a lot of connotations, and unfortunately a lot of negative connotations. And that primarily comes from this asymmetry between, the good tier and the bad tier in performance. And to go one step further, it's the asymmetry in read performance. And so that's really why I drew that distinction between CMLC or MLC in general and TLC, is that there actually isn't really a difference in read performance. And what that means is that if you introduce it into a system, there isn't tiering. Right? You can have CMLC alongside of TLC, and it doesn't really matter where the data is. The experience that's delivered to the end host accessing the storage is consistent. And the story on the writes, what makes all of this tick, and what I sort of wanted to dive into, is that it's really, there's a latency bandwidth trade-off. And if you can do a good enough job in delivering low latency back to the hosts when accepting incoming IOs, and then really use the bandwidth that's present in SSDs, we'll talk about some of those trends in a minute. But if you can use the right bandwidth that's present in the SSDs, you can present a great write experience to the user from a latency perspective and from a bandwidth perspective, and still be able to tolerate on the back end variability in write latency between your SSDs. You have a CMLC drive that presents one write latency, a TLC drive that presents a different write latency, and if you have the proper pipelining in the system, that doesn't matter one bit to the user. So we can go into some of the details there. Before we do, does everybody around the table, do we know the difference between CMLC, EMLC, SLC, TLC?
How do you handle the reliability, or the relative reliability between something like CMLC and EMLC?
Okay.
And is it like factor of 10 difference? Is that endurance-wise kind of thing?
Right. So I think that is really the crux of the different kinds of flash, is really the reliability. So to just level set here, the actual semiconductor die that you get across these things is more or less the same between, going all the way from SLC down to TLC and all the flavors in between. The things that are different are binning, and yes, binning makes some difference. It's not the first order difference. Obviously, between SLC and MLC, it's how many bits per cell. That affects your performance, because you have to be able to program the cell more accurately to store 2 bits rather than 1 bit, and similarly, going to TLC to program 3 bits rather than 2 bits. But the main difference, if you look between a CMLC and an EMLC, is really the amount of flash that's present in the SSD. Everybody in the room, being a storage guy, of course, knows about over-provisioning. And that's really the amount of extra hidden storage you have inside of an SSD. And that extra storage is there to deal with overwrite. And an EMLC drive, the main distinguishing factor from a CMLC drive is the amount of over-provisioning that's present. Now, it turns out that the wear on an SSD assumes a certain write amplification. And it assumes a fairly high write amplification. I don't know the exact number, but I think it's somewhere between 8 and 10. And that assumption really comes from the idea that you take the SSD and you pull out a spinning magnetic hard disk and you place the SSD in. That's where that 8 to 10 assumption comes from for a consumer grade MLC drive. That write amplification goes down if you add more over provisioning. Not only does the write amplification go down, the writes are spread over more flash, and it's those two factors combined which yield the longer lifetime of an EMLC drive. Well, it turns out that if you use your flash properly, you don't get a write amplification of 8 to 10. In fact, reading the smart information that are on the SSDs, we see about a write amplification of 1.1-ish, right, in that ballpark. So what does that mean? That means out of the box, the lifetime that we're getting from our SSDs is roughly 8 to 10 times longer than what the manufacturer expects.
At a high level, how do you achieve that?
Right. So the 10,000 foot view of how to achieve that is to never do an overwrite in place. So write amplification is created when you do an overwrite in place and you poke holes in a bunch of data all over the SSD, and then you're forced to copy the remaining data to create a free erase block. So what we do in our system is more or less we write to the SSDs in a way to neutralize the garbage collector that's built into the SSD's firmware.
It's like a log structured file system?
It's basically a log structured file system. And so by neutralizing the garbage collection that's happening on the SSD, you remove that write amplification. We then manage over provisioning and we manage garbage collection at a system scale. Right? So rather than doing it, in our smallest system, we have 22 SSDs. So rather than having 22 SSDs making independent myopic decisions about how to do garbage collection, we have these smart controllers sitting up here looking globally across those 22 SSDs, deciding how to make garbage collection decisions.
And doing that doesn't add a huge overhead to the CPUs in your controllers then?
Well, of course it takes CPU, but the secret sauce, if you will, the reason why this floor and the floor below me is filled with engineers is to really manage that trade-off, right? To figure out how do I spend these CPUs to do compression, to do dedupe, and to also manage the lifetime of this flash. Right? At the end of the day, those are the things that we're in charge of. Right? We need to be affordable, so the other part of the secret sauce, so using consumer-grade hardware makes it cheaper. The other part of the secret sauce is, of course, doing data reduction. We bet very early on and have held steady on this that you need to do dedupe, but dedupe only takes you so far. Dedupe does not do a whole lot for you for a single database application. So we've bet that you needed compression. And so from the very beginning, our platform was one that supported dedupe and compression. So that's the other piece of the secret sauce on affordability. But in addition to these CPUs delivering to you affordability, they're delivering to you reliability. And the way they're delivering to you reliability is by doing this global garbage collection and doing this
You say global you're actually controlling the garbage collection done at the SSD level, or you're doing garbage collection at the system level?
So
across all the SSDs?
The answer is basically yes to both your questions. And so the reason why I say it's yes to both is because we've more or less reverse engineered the firmware on these drives. We can't change the firmware, but we've reverse engineered the firmware. So we write to it in a way that's going to make this guy's garbage collector behave the way we want it to behave. We can't turn it off. We'd love to turn it off. But what we're basically trying to do is write to the drive in such a way that when it needs to find a free erase block, what it concludes the vast majority of the time is I have a completely free one, I just erase it and move on.
So I'm fairly sure that there are other vendors out there that have custom firmware, or they write their own firmware for drives. It just sounds like the way your reverse engineering sounds like quite a lot of work, and then if they bring out a new version of the controller and a new version of firmware, do you have to start from square one again?
So it turns out that, first of all, you're right. There are other vendors out there that do have custom firmware on SSDs. So there's a couple aspects to this. One is, do you want to be using the best and the latest flash, or do you want to be a little bit behind in generation because after they do the die shrink or they do the new process, develop their own firmware, you might not have to wait till they fully release it into the market, but you're not the person getting access to first sample designing and implementing the new firmware. So we've opted to say, yes, it is difficult to reverse engineer these things, and yes, we do need to reverse engineer each new one as it comes out. But the second aspect of it is, luckily for us, there isn't a huge amount of variability and a huge amount of optionality, if you will, in how to design one of these things. So what we have is a fairly flexible framework, and thus far we've found that across 3 or 4 generations of flash media from a variety of different flash vendors, we've been able to essentially fit it into our model and get it to behave the way we want it to behave. So it's not like we start from square one and have to write all brand new software every time this comes out. It's also we have a modular hardware architecture. We also have a modular software architecture, which means that this effort to retune to a new SSD is constrained or confined to some of the lowest levels of the operating system stack.
This is also a process we just wanted to be very good at. We always wanted to be multi-vendor supplied. Our arrays ship today with multiple vendors, and we wanted to be able to mix and match lots of different types of SSDs over a generation of deployment. And so if a customer had one of our arrays for 5 or 10 years, there might be 15 types of drives in that array, and that should be fine.
And I mean, one of the things we haven't talked about is that the way the architecture is built, I show one storage shelf here, but you can attach more than one, obviously. It's a single pool of flash, right? And so some of the simplicity that we get is because you are not in the business as a storage admin of taking your volume and pinning it to a disk group of any kind. And by no means is that unique to us. That seems to be the norm in the purpose-built all-flash arrays. But it's important, to Kix's point, that when you buy this and then you want to come back to us and buy an expansion shelf, there's a pretty good probability we're not going to be able to give you a shelf with the same SSDs that you have already. So we have to be able to deal with the varying characteristics of the different drives and still deliver a consistent, fantastic user experience coming out the top. I didn't draw, the host over here speaking Fiber Channel or iSCSI getting into the box. We have to deliver the same or improving user experience up here, even though down below we might have a variety of types of flash. And, to the question over here, that might in the future include not just MLC, but it might also include TLC flash.
So you were saying earlier that you don't overwrite your blocks. You create a new block and then move pointers. Is that
That's right.
Correct? Okay, so what happens when the array itself starts filling up? Doesn't that make garbage collection more difficult because when you do a block erase, it's harder to find open blocks to do that garbage collection?
So it turns out if you look at the mathematical properties of when you expect blocks to be completely free and other things, there's a relationship to the amount of over-provisioning you have, but there's also interesting statistics in that you have a tail, if you will, where even though the average block maybe is X% empty, you actually have a tail to this curve that is far emptier than that. And it turns out those are the blocks that you really want to garbage collect, because those are the ones that are really cheap to garbage collect. And so the larger your sample set that you can look for that over, the more likely you are to find those blocks and the more likely you are to find great blocks. So I think your question, though, is it hard to find those blocks? There's a whole lot of them, and you got to go rifling around looking for them. And the answer is, well, it all depends on what data structures you use under the hood. What does your metadata engine look like to help you find that information? And you look, fundamentally speaking, once you introduce deduplication into an architecture, whether it's ours or any of our competitors, you have some amount of free block tracking that's promoted itself to the system level. Because just because a single user block was overwritten doesn't mean anything for a corresponding physical block. There could be 20 other references to that physical block. So the game of free block tracking happens everywhere. The other aspect to this that we haven't spent a lot of time talking about is how do you implement RAID. And in our approach where you don't overwrite data in place, we have a unit called a segment. The segment is made up of multiple SSDs, and our RAID is segment-based. So you can think about a segment as just being a chunk of data in a log-based file system. It's that notion of segment. And that's where we implement RAID. So because you never overwrite part of a segment, you never get any of the write amplification that's associated with RAID. So if you think about RAID 6, you want to modify one page, well, you have to modify not only that one page, but you have to modify 2 parity pages when you do that in place. And whether you call it RAID 6 or you put a marketing name to RAID 6, fundamentally, if you want to do double error protection, you're going to be doing some erasure coding scheme where you have 2, I'll call them parity shards, but you're going to have 2 parity shards. And so once again, whether it's because you're doing system level garbage collection as we define it, or you're doing something else, pretty much everyone out there is doing optimizations so that they can find the most empty RAID stripe, and then they batch their writes so that they can jam them into the most empty RAID stripe so as to minimize that write amplification. Because I said if you want to modify one page, you have a 3x amplification. Well, if you want to modify 10 pages across a stripe, well, now you're doing 12 writes to support 10. That write amplification went way down. So pretty much everyone out in the industry who's doing Flash has more or less come around to our formula for what we're doing, and that you do have to manage free space at the system level. You have to be cognizant of that. Dedupe and write amplification make you do that. It just so happens that since this was our formula from day one, we got the benefit of getting really granular compression along, that goes along for the ride. What do I mean by that? Well, if you take an architecture that has some fixed block size, and we don't have a fixed block size, and I'll get into that in a minute, but if you take, let's say, 4K of data and you compress it down, you don't get some nice even multiple of sectors out, right? This 4K can compress down to 375 bytes if it's really redundant, or 3,750 bytes, or anywhere in between. And because of our architecture, we don't create a complicated bin packing problem of looking for free space that's exactly the right size. We're just taking the compressed data and putting it into these segments, these log structured segments, and that creates holes in other segments because there's data that's no longer referenced. And when that segment becomes sufficiently empty, we garbage collect it. So we've taken a lot of problems that people have, write amplification for RAID, dealing with dedupe and the liveness of physical blocks, the round-off error in compression, and we've just turned that into one problem that needs to be solved. And so the folks that are out there that are claiming that they don't do system-wide garbage collection, and they rely on the SSDs, I mean, for better or worse, what I really hear is we don't benefit from doing system-wide garbage collection, but we do it anyway. Right? That they haven't decided to make that one integrated part of the architecture, recognize that to leverage flash, that's something you must do, and then own it and make it first class in the system. And
Basically saying that your dedupe is actually part of your garbage collection. Is that what you're saying?
Deduplication is not part of garbage collection, but garbage collection is dedupe aware. Right? We're not going to collect a block that is that's being referenced unless most of its peers are garbage, in which case we'll move it.
It would be helpful if you could just kind of go through an I/O flow in the system and give people a sense for kind of how it works in that sense.
Yeah, that's great.
So is it as well when you? I'm trying to do Twitter and stuff as well. When you do garbage collection and you move data around, that data goes through the dedupe engine anywhere. Anytime you write to the flash, does it go through the entire stack of dedupe, compression, and what have you again?
So that's an option that we have. Why don't I go through the life cycle of a byte of data or a sector of data, and I think it'll answer that question pretty simply. So when data comes in, so this is a host over here, and he does a write. The first place that data lands is into NVRAM on our platform. Now, we haven't talked a whole lot about the NVRAM yet, and we can go into more details on this. If you allow me to gloss over it for the moment, we can come back. But just know that this is NVRAM that we put into our storage shelves rather than NVRAM that's in the storage controller. And that actually gives us a stateless controller, which gives us a bunch of simplicity, which we can talk about later. Once the data is written redundantly in NVRAM, we can go back and acknowledge the host. From his perspective, the write is done. From our perspective, the write is safe because it's in media and it's in media redundantly. But from here, we actually have to take the data and somehow move it to SSD. So this is where we do the first round of data reduction. And what we have in round one of data reduction is inline dedupe and a medium weight compression.
And is it in that order? Does dedupe then compression?
Absolutely. So you want to get rid of the blocks that are already somewhere else. Those turn into metadata references, and you only want to spend your CPU compressing what's left.
That was the opposite to the guys yesterday, yeah?
Okay, that's surprising. But
Yeah.
the goal here is to try and get rid of as much duplicate data. Right? If you think about it, turning a block into metadata is the best darn compression you're going to be able to get, and what's left over, you compress. Because, of course, there was a time when that data that you're making a reference to, well, it didn't make it through, it didn't find a duplicate when inline dedupe ran, because it was the first copy of it. And that time around, it went through this compression algorithm. So your dedupe is already referencing compressed data, but it's really the unique data that you want to push through compression. At this point, the data gets batched up into the segments I was talking about, and lands redundantly into SSD segments, and those are protected with RAID 3D. So RAID 3D is a double error correcting RAID system, so we can tolerate 2 drive failures, etc. The other thing that we do with RAID 3D is we recognize that SSDs out there can be quite finicky. And Depending on the exact model of SSD, if you try and read from it and write to it at the same time, you can get some unexpected performance results on your reads or your writes. So there's models of SSDs out there where if you read while writing, the reads go glacially slow. There's models out there where if you read while writing, the reads will perform the same speed as the writes, which means they're slow, but they're not glacially slow. There's models of SSDs out there where if you do reads while writing, it interferes with the writes and the writes start going slow. Because of that, because we have this double error correction, we can actually set up a system where if we see reads and writes interacting negatively, we can stop reading from certain SSDs and say, if you want to go access that data, just do a RAID reconstruct. It also gives us confidence that our RAID works because it's happening hundreds of thousands of times per second. So there's no surprises when there actually is any event with an SSD. We know we've been writing down the correct RAID information because
So
we would have known.
you're going to read the whole stripe to recreate a block.
That's right. So that's one of the beautiful parts about SSDs is read bandwidth is more than abundant. And so if you have to throw an extra couple reads at a problem, no big deal. So by the time the data makes it into these SSD segments, we can then free the space in NVRAM, and you actually begin to notice a really cool property of our architecture, which is that once the data is ingested and written redundantly, the entire life cycle of data from there on forward is what I call a leapfrog, where you write it down a second time and then erase the first one. So there's no moment in time where your data isn't persistent and isn't protected. That's really what gives rise to our extreme confidence in the reliability and the availability of our architecture, so much so that our proper shutdown procedure is to go to the back of the array and yank power. There's no complicated shutdown because there doesn't need to be. That once the host has its I/O acknowledged, you always have redundant copies of that I/O. Now, what can we do from this point? Well, there's two different tacks that the data can go on, and I don't mean this to be an either or. Both of these are happening concurrently. So one of them is background dedupe. And this I'll call data reduction round 2A. So what is background dedupe doing? Well, it turns out that our back-end architecture does not have a fixed block size. Our front end doesn't have a fixed block size. Everything is variable, with the sort of the unit obviously being the unit that you talk when you speak SCSI, which is a single sector. And what that means is that there's no such thing as perfect dedupe. You can find that you have data that overlaps in interesting ways. That I could take the first 4.5 kilobytes of this write and dedupe it against something on the left, or I could take the last 6.5 kilobytes and dedupe it against something on the right, and those left 4.5 and the right 6.5K might have actually overlapped a little bit. And so there's no perfect decision here. You can do partial references, and there's a whole lot of other things that you can do, but it means that searching for how you wish to represent the data is a much more challenging problem than the world where you just say, I'm going to carve up my data into fixed size aligned blocks. Do I have this block somewhere else? And so because of this variability, we do basically enough dedupe on the front end till we hit the point of diminishing returns, and we soak up extra available resources on the back end looking for more dedupe opportunities. Now, the reason why we're comfortable doing this background dedupe, and notice I haven't mentioned garbage collection, outside the context of garbage collection is because if this guy over here finds more dedupe, all he has to do is write down metadata. writing down metadata does not lead to significant amounts of write amplification. You're not taking the data and writing it a second time. You're writing tiny, tiny, tiny bits of data. Now, this will poke holes in other pieces of the system. So this is a, if you will, a garbage creating process. No different than writes that come into the system and overwrite a piece of data. The other path here is garbage collection. So as data gets overwritten, we have some segments which are basically split up into pieces. They have live data and they have dead data. We're waiting to find segments that are basically majority dead, and we take the remaining live data and we write it down again. Now this is data that's survived long enough, and so rather than applying a medium weight compression as we're moving that data, we apply a heavier weight compression.
Neil?
Yes?
So that medium weight compression, which algorithm is it?
All of these are basically variants of there's an entire family of Lempel-Ziv-based compressors. These are variants of those, some of which are publicly available, some of which are homegrown internals.
Because there's just been a moderately large discussion on Twitter around whether or not compressing before deduping is the right way, or whether deduping before compressing is the better way. And people are just asking now, well, maybe it depends which compression algorithms you're using.
Right. So some of the motivations for saying, well, hey, back up, I want to compress before I dedupe, is to not disturb the data. Right. If there's certain patterns in the data that if you cut out the middle, you disturb, and then the compressors don't capture that. So, I don't want to point to theory and then hide under constant factors that are in those theory, but if you look at Lempel-Ziv and the various forms of Lempel-Ziv, and you look at Burrows-Wheeler BZIP compression, these are what are called asymptotically optimal compression algorithms. So what that means is it's sort of fancy speak for if you give it a large enough block size, it will reduce the data to the minimum amount of size. It'll reduce it to the amount of entropy that's in that data. Now, like I said, I don't want to hide underneath that because the size of block matters a lot. It also matters, there's a constant factor that rides in there. But at the end of the day, if you look at a lot of these compression algorithms, the off-the-shelf ones, they do a remarkably good job at reducing the data to close to its minimum form without knowing about other structure or without going lossy. And obviously, when we are a block storage array, lossy compression algorithms are removed from the table. We don't do that. I don't think, short of getting direct instructions from an application through the protocol, we would ever, be even able to do that without having, without being strung up to
Neil, is the
somewhere.
background dedupe, does it require to read the data again, or is it can be done through just metadata?
That's a great question. So let me just finish up on the compression. So the reason why we don't worry too much about cutting out data with dedupe is because of the quality of the compressors. So what we do regarding the background dedupe is an it depends answer. So we're using primarily metadata to guide us to finding duplicate blocks. But one of the pieces of the architecture that we decided on fairly early is that we're not going to use strong hashes, in the sense we're not going to use cryptographically strong hashes. What that means is that just because two blocks have the same hash does not mean they're the same block. And so we have to be able to go back and read the data in order to confirm byte by byte that it in fact is the same data. It goes back to the point of lossy compression almost, that a hash is a form of compression. It's a form of lossy compression, in fact. And we don't just rely on that lossy compressor saying, the probability is 1 in whatever, that it's the same block and that probability is good enough. Probably 1 in whatever that it's not the same block and that probability is good enough. We actually go and compare the data. what that flexibility, what that choice gives us, though, is the ability to budget our DRAM the way we want to budget our DRAM. And you'll notice that compared to some of the other folks out there, in a fixed, pair of controllers, the amount of flash we're able to manage is considerably greater than what other folks in the market are doing. And a lot of that comes back to design decisions like this, right? So our metadata is not completely in DRAM, and our dedupe metadata, which you'd really like to be able to access efficiently, especially up here in inline dedupe, we actually have control over how much metadata there is, even for larger and larger footprints, because we're not relying on a cryptographically secure hash in order to do our dedupe. What that ultimately translates to, remember I was writing those value propositions, it means more affordability, because you can get to larger and larger capacities without having to spend money on more compute, more controller horsepower at the front end. And you get to amortize the cost of those controllers over more and more capacity, and you get to deploy more controllers and when and if you need more performance, not just to be able to manage more storage. So let's see, we've jumped quite a bit around, and I've used about an hour of time. Are there other areas that you want me to dive into? I can quickly just run through an outline to see if there's anything significant that I missed. But I'm happy to take more questions as well. Let's see.
So, are any of your customers asking, look, I saw Matt's slide earlier on, right, and this probably sucks as the kind of question I should be asking, but are any of your customers asking for a more scale-out architecture?
Absolutely. So a lot of customers, I think, are asking for scale-out architectures when we get into the initial phases of discussion with them. And then after we have an actual discussion, they begin to realize that scale-up versus scale-out is not even a sensical question to ask. And the reason for that is, what problem? Like we just really go back to them and say, what problem are you trying to solve? And when you basically push that question in front of them, you come down to 3 reasons for really caring about the direction you scale. They're worried about how much capacity can I get within a single array. They're worried about how much performance can I get within a single array. And they're worried about how much reliability can I get within a single array. All of this while being worried about the cost of that same array. And it turns out that most of the customers that we talk to start getting uncomfortable, no matter how resilient your architecture is, they start getting uncomfortable when they put more than half a petabyte to a petabyte of storage under control of one array. And I like to just point at our history rather than our future. That the first product that we shipped, after you guys were here the last time around for the storage field day, it was a 5.5 terabyte product. Today, the largest product we shipped is 70 terabytes. So right there is a greater than 12x growth in the amount of raw capacity we've been able to manage under our current architecture. Now that 70 terabytes raw translates today to rough and tough, if you're looking at average data reductions, to a 1/4 petabyte of storage. So we're not that far off in the landscape between getting to that 1/2 petabyte and 1 petabyte mark, where scale up, out, diagonally doesn't matter. People don't want it in one array. So then you come to the other aspect of the architecture, which is performance and reliability. And it turns out that there are some folks out there that have solved the reliability problem, but in solving that reliability problem have created a cost problem. Right? They do things like triple mirror rather than using erasure coding and other things. There are other people who've built scale-out architectures where they actually their reliability decays as they scale out. This is the scaling out HA pairs. Simple reliability math tells you that if one pair is 5 nines available, if you have 2 of them, 3 of them, 4 of them, have a cluster of them, it's not long before you get to 4 nines available. If you have one pair that's 6 nines available, it's not long before the cluster gets 5 nines available.
But that's only if your architecture scales out in pairs.
That's what I'm saying. That as far as I've seen in the market, there have been 2 strategies. There have been what I'd call the true scale out, and those guys haven't done erasure coding. They've done a lot of redundancy.
Is that a problem, though?
So it's a problem in terms of cost, right? If I want to be able to survive 2 SSD failures, I'm doing triple mirroring of my data. I'm paying triple in my raw flash costs. The amount of flash per node that they manage tends to be lower, so I'm paying a ton in my controller costs too. So I have really, really high expense to get basically to get that level of reliability, to get more reliable as I scale out. And we haven't even talked about the performance considerations there, about the just different cluster level synchronization mechanisms you need to make sure that you have data consistency. It turns out also that a very common failure mode for complex systems is the software, not the hardware. And so as you scale out, and I said that there's complex systems to get consistency, those might be the things that are at risk of failing, and you might have failures that ripple through the cluster. Now, I'm not saying that this is an actual vulnerability that anyone has, but it's something that you should be cognizant of when thinking about an architecture. So the other design that people have done is this cluster of HA pairs. And the reliability is really in an HA pair. And if any pair fails, the whole cluster goes down. And there, as you scale, you're getting less reliable. So you boil this all down, and what you're left with is the only reason to truly care about a scale-out architecture is performance. And the vast majority of our customers are hard-pressed to push the performance envelope of what we ship. And so once you get to this, they realize that they're asking the wrong questions. And what they really want to do is go from vendor to vendor, including us, and ask, what's your reliability? What is your biggest capacity scale? What's your biggest performance scale? And then see how well that fits into their infrastructure, given the dollars per gigabyte. And we found that when customers do that math, a lot of them are picking Pure as the solution.
Some vendors use an VIP to virtualize the transport, so you can have a federation of multiple arrays. Are you planning to do that? Because it could help. It's not a scale out, but you can move LANs all around.
So to be perfectly honest, we think that that's really where the future lies. And the reason is because you can have, as you're pointing out, you can have independent failure domains, so you don't lose multi-petabytes amount of storage if catastrophe happens and you lose an array, but at the same time you do keep the flexibility of more or less having a single pool of storage. You don't have to worry about, well, how do I get my data from over here to over there to consolidate my free space or anything like that. A lot of people today enjoy the effect of that because VMware does a fantastic job of giving you that transparency. That being said, we don't want to take sides in any sort of data center debate about how it should be architected, should you have a hypervisor or not. And we would love to be able to provide that functionality at the storage layer so you don't even think about it and you can transparently move data. But that's something that we've actively considered.
Question about sort of the hardware architecture. So if I have one of these systems and I have, I'll just make up an arbitrary number, let's say 10 host interfaces running at a particular speed. And I look at all the drives in the front, or in the back end of this thing, and each of those drives has a certain amount of bandwidth available to it for delivery. Is there anything in the middle of the box, SAS expanders or anything else that would maybe be a choke point instead of the ends?
That's right. So the question really is about speeds and feeds, and you know, if I sum the back end bandwidth and sum the front end potential bandwidth, are one of those two things ultimately my limit in performance? And the answer is no. There's always something in the middle that ends up being the bottleneck. Now, it's not things like SAS expanders or other things. It's actually much simpler. The question was I think, raised over here. It's the CPUs in the system. So you're doing a lot of complex metadata manipulation. You're doing data compression and decompression. You're doing deduplication. The CPUs are ultimately the bottleneck for what limits the performance scalability of the system. Luckily for us, just down the street, Intel works very, very hard and very diligently consistently on delivering considerable amounts of performance year in, year out. We are fortunate enough that our entire software architecture was built up in the multi-core era, which means we're not jamming parallelism in after the fact. It was built from the ground up to be an extraordinarily parallel system. So every time Intel either releases faster cores or more cores, we benefit from it. And we've been able to keep up pretty well with the rate at which folks are demanding performance by revving through generations of controllers. And we launched with the FA300 series, then went to the FA420, and then came out with the FA450. Each of those generations has delivered considerably more performance than its predecessor.
So can you, Intel ramps the processor, can you just simply put a new processor on there, leave all the rest of your stuff the same, and it just automatically picks it up?
One of the things I alluded to was that this NVRAM's in our storage shelf, and what that leaves us with is a completely stateless controller architecture. So you can do a non-disruptive upgrade of hardware or software, and it's really cool, something we're really proud of. You can take a controller, pull it out of the system, put in a replacement, and it gets its entire identity from the storage shelves. It's metadata just like any other, and that goes down to the fiber channel WWNs. So when you do that upgrade, you're not sitting there rezoning your entire fabric or teaching your hosts about these things. You just drop it in and it's ready to go. We've had customers do this upgrade in the middle of the business day on their production Oracle instances that back, a pretty top tier public facing website. And without a hiccup, they just keep going. And that's kind of what we want to be able to enable, that not only should Flash enable better storage experience from my IOs are faster, Flash should enable an entirely better experience for the people managing it too, where you don't, basically spend your time, effort, energy figuring out how you're going to execute an upgrade or how you're going to forklift from here to there. We want you to stay on the same array for a decade and just move through the hardware and software generations with us without ever taking a second of downtime. And that's really the cornerstone of Forever Flash, which is, the business model married with the engineering background. We want storage to be simple. As Kik said, it should be invisible to everybody but the storage admin, and it should be simple for the storage admin. And I'm not convinced the storage admin should remember it's there either. So.
Well, I think one of the nice things about a lot of this flexible upgrade and stuff is it just works today, right? And so it's reliable, it just works, customers are trusting it for us. And I think the other thing I'd say in the debate with scale out is there's quite a bit of difference today in the market between the theory of scale out and the actual vendor reality implementations. And so, we're in a zone where a lot of those vendors are still struggling with basic things like adding nodes to their clusters and maintaining availability of the systems and whatnot. So, I think we've been able to find that we are able to get to market with a very reliable system that scales to a cluster size that's big enough for almost anybody. And our multi-petabyte size customers, they're not asking us to put it all together in one big multi-petabyte array. What they're asking for
asking for us to not do that.
What they're asking for is what was brought up earlier, which is solid management federation, data service federation between nodes, and that's what our roadmap's going to be.
Neil, the write blocks mirrored across two different drive shelves, NVRAM, or how's that?
So it's mirrored, when it comes in, it's mirrored across two different NVRAMs. We consider all our NVRAMs in our flash to be a single pool. So it's not mirrored across different storage shelves, if that's what you're asking. It's mirrored across different SSDs.
Hey, we've asked this question a few times at different places, so it's getting a bit old hat, but what about vVols from VMware? And actually, maybe what about other protocols like file protocols?
So if we get there, we're going to show you a demo of vVols.
Oh, perfect. I was going to say, yes, we like the vVols. One of the benefits you get of having a completely virtualized storage infrastructure is if you want a virtual volume or a real volume, it's like, it doesn't make a big difference to us. We just have to teach our box new tricks in terms of being able to speak VASA and being able to speak extensions of the SCSI protocols.
We have customers asking for QoS mechanisms because you deliver a lot of IOPS, but sometimes the kind of application that they use are really hungry.
Yeah, our main goal is, I think, to address the case that you just mentioned, that if there's one or two outlier applications that are super hungry, to be able to make sure that they can't interfere with everybody else. And so that's something that's on our roadmap that we plan on delivering. Much with everything else that we do, we want it to be simple, and we don't want you to have a PhD in QoS in order to be able to use it. All of our features are always on, and we'd like all of our features to always be always on. So we don't want to ship a QoS that's this thing where, as Matt was alluding to earlier, where you check a checkbox saying, yeah, I got it, and nobody uses it. We want something that actually delivers value.
Are you going to stay with Dell servers or look at creating your own design?
We'll look at whatever makes sense, I think, is the
We've
simple.
had multiple suppliers in our history, and we'll always look at multiple suppliers for everything we do.
So I think something like a vVols demo will be more exciting than probably the nuances I can get into. I'm happy to answer any more questions if you have last ones, but otherwise I'll turn the floor back over to Matt and Vaughn.
How many solid states have been returned over the last 3 years?
How many SSDs?
Failures, yeah.
I don't know the exact number, but it would be, I believe it's less than 5, but I don't know for sure. Do you happen to have the number off the top of your head?
No, this was one of the old-timer questions that came up in our first storage field day, and so I think it might be more than that now. But if you look in a world of normal hard drive failure rates that can be measured in the whole percentages, we're well under 0.1%.
I'll say that in terms of an actual true media failure, I believe we would have 1.
Yeah, that's a good point. When SSDs fail, they fail for software, not because the hardware failures.
And that comes back to the other question of why not custom firmware? Because the stock ones work much better.
Do you have a number of the customer already deploying your system? So
That's a Matt question.
Yeah, so we're well up over 1,000 units shipped at this point.
how many?
Over 1,000 units shipped, yeah.